Let's welcome paper ID 428. Matthias Seibold is a PhD candidate at the Chair of Computer-Aided Medical Procedures at TU Munich and the Research in Orthopedic Computer Science Group at Balgrist University Hospital of Zurich. His research involves the fields of deep learning, acoustic sensing, computer vision, medical, augmented reality, and surgical sonification. The title of his speech is Improved Techniques for the Conditional Generative Augmentation of Clinical Audio Data. Dr. Seibold, please share your screen.
Thank you for the kind introduction. Okay. All right. So yeah, thank you for the introduction. My name is Matthias Seibold. I'm a PhD student at Computer-Aided Medical Procedures Chair at Technical University of Munich, and I'm also working in the Research in Orthopedic Computer Science group at the Balgrist University Hospital in Zurich. Today I'm going to present our paper, Improved Techniques for the Conditional Generative Augmentation of Clinical Audio Data. That's also a collaboration between the camp chair at TUM and the ROX group in Zurich. So what is acoustic sensing? I guess you can hear that this sample corresponds to a person knocking on wood. And by listening to this example, you probably noticed that this is a sample of or audio recording of someone knocking on a thin sheet of metal. So this is a simple example that illustrates how much information is contained in acoustic signals and how powerful the human hearing is to actually infer a lot of information only by listening to a small or like a short recording of audio signal. And combined with high quality recording hardware, advanced signal processing and analysis methods that are based on deep learning as well, acoustic signals can be also exploited for medical applications. So let me give you a few examples of our own previous work. In this project, we developed a system for instrument tissue interaction classification by analyzing coagulation sounds in minimally invasive surgery. And you could hear in this video, you could hear the sound of the coagulation. We proposed a drill breakthrough method, a detection method that uses structure-borne acoustic signals that we captured with a contact microphone that were contact microphones that were placed on the patient's or specimen skin, and we could achieve promising results. So we could detect the drill breakthrough based on the analysis of the acoustic signals with sensitivity up to 94%. And here we developed a system for the evaluation of the optimal insertion endpoint of femoral stem implants in total hip arthroplasty, where we used a contact microphone that we attached to the inserter tool and used a sequence of 5 acoustic signals of hammer blow events that were analyzed using a spatiotemporal deep learning model. So this brings us to the motivation of the present work. So acoustic signals have been shown to have great potential for real-time surgical error prevention, for multimodal sensing applications in surgical navigation, for example. They can also be used for workflow analysis and provide additional sensor data for robotic applications. But it has to be stated that clinical data is often very expensive to acquire. So for a lot of projects that are related to acoustic sensing, you have to perform cadaver experiments to record data sets of realistic audio recordings, or record data in the operating room, which is also associated to ethics and to regulations and limited access to the realistic environment. So classical data augmentation techniques or data augmentation in general is a very important tool to overcome or improve the data bottleneck here. And for audio signals, classical augmentation techniques are, for example, time stretching or pitch shifting, adding Gaussian noise, or also spec augment, which has been proposed by Google, which is a spectrogram-based method. But these techniques generate samples that cannot be captured in the real situation. So a possible solution for this would be to design a method to sample new data from a learned dataset distribution. And there's also a body of work in the field of generative methods for data augmentation of audio signals. So Hu et al. Proposed GAN to synthesize F-bank features of speech data. Madhu et al. Proposed a method that uses separate GANs for synthesizing MEL spectrograms of each dataset class for an acoustic acoustic signal dataset. Then the balancing GAN framework was applied to augment an imbalanced speech dataset. And in our own previous work, we proposed a conditional GAN that is able to augment clinical audio data in the form of MEL spectrograms, which is one of the most used feature representations for audio data. So in this work, we propose an improved generator architecture that implements residual squeeze and excitation modules, which is trained on a data set recorded during total hip arthroplasty and on MEL spectrograms computed from this data set, which is able to synthesize new data samples from the learned target distribution. We trained the model using Wasserstein laws with gradient penalty regularization and determine the stopping criterion by assessing a custom version of the threshold inception distance. We evaluate the method based on a data set that was recorded in the real world operating room in our university hospital. And yeah, so this was published in previous work. And we evaluate the performance of the augmentation method based on the classification performance of a ResNet 18 classifier. So the previously published dataset contains audio recordings of typical surgical actions in total hip arthroplasty. It contains 6 classes, which are suction, coagulation, sawing, reaming, implant insertion, and implant adjustment. And you can see here in this overview of the dataset how the classes resemble the different phases of the intervention over the course of the whole surgery. So this is kind of resembles the surgical workflow. And the dataset contains 568 recordings with a length of 1 to 31 seconds and is publicly available. So the proposed improved generator architecture implements 4 convolutional layers and 3 residual squeeze and excitation modules. And the modifications result in a parameter growth of only 0.74% compared to the previous version of the architecture. So let us have a close look into the residual squeeze and excitation module, how it works. It consists of 3 basic operations. The first one is a squeezing operation, which is essentially a global average pooling along the channel dimensions. Then an excitation step, which is a gating mechanism with a sigmoid activation, which consists of 2 fully collected layers and acts as a channel-wise attention mechanism or also channel-wise feature recalibration mechanism. And lastly, channel-wise scaling of the original feature map by multiplying it with the obtained excitation map. Furthermore, the module also contains a skip connection similar to the classical ResNet module. So here you can see real spectrograms in the top row, like original samples from the data set, and generated samples in the bottom row, generated samples by the proposed model. And it can be observed that the model is able to generate high quality class conditioned samples from a learned target distribution. To analyze the effect of the residual squeeze and excitation modules, we computed the channel-wise correlation of the learned latent features that are visualized here as correlation matrices. The analysis revealed that the squeeze and excitation modules reduce the redundancy of the learned features and help the model to learn more robust features during the training process. So a higher value, the brighter values here in this plot correspond to higher correlations along the channel-wise features. So we show that our model outperforms all previously suggested, previously proposed audio augmentation methods, both in terms of threshold inception distance, where the lower is better, and classification performance that we measure as the mean macro F1 score over in a 5-fold cross-validation experiment, and we report the mean and standard deviation over the cross-validation experiment. And yeah, so we compare the data set with no augmentations, classical audio augmentation techniques, spec augment, the previously published method, and the proposed method in this work, and we can show that we outperform the best previous method by a margin of 1.14%. To conclude, in this work, we proposed an improved GAN architecture that is able to generate high quality synthetic samples for the augmentation of clinical audio data. We outperform the best previously published method by a margin of 1.14%, which is almost a doubled performance gain. Our proposed augmentation method is therefore an important step to improve the data bottleneck for the design of deep learning-based medical acoustic sensing systems. So thank you very much for your attention, and I'm happy to answer questions.
Thank you. Thank you, Dr. Matthias, for his excellent speech. If anybody have any questions, please feel free to ask.